Good day, mathematicians, statisticians, IB extraordinaires. Today we're going to look at discrete random variables very quickly and talk about finding some of the parameters for a discrete random variable. And to do that, we'll look at an example. Let's start with a game that comes from this little spinner. So I drew a little circle, and I'm going to cut this circle up into 8 evenly sized slices, and you just have to pretend that's even. And I'm going to start assigning some values. So let's say that you spun the spinner and you got, say, into this spot or this spot or this spot, you got a 0. Let's say, in fact, any of, maybe this spot as well, and maybe this spot as well. Any of those 5 spots, you would win 0. So let's define W as sort of the amount won when you spin this spinner exactly once. And let's write the possible values of W. So the first thing is you could win nothing. Now let's say in these 2 slots here, let's make it a little bit more exciting. Let's say in those slots you could win $8. So that was another possible amount. I'll write $8. And then finally, maybe in this slot right there, let's make it interesting. Let's make that $24. So that's 24 possible dollars you could win. So in this table, we now have the 3 possible values of W. Let's now write the function P of W, and it will define the probability of each of these events happening. So if we take a look, there's 8 spots. So getting a $0, that's 5 out of the 8. $8, that's 2 out of the 8, which is of course 1/4, but or 24 was 1 out of 8. But I left it as all 8 as a denominator, so it's very obvious that 5/8 plus 2/8 plus 1/8 equals 8/8, which is 100%, which means this is a valid probability distribution, which makes us happy. So now let's find what we'll call the mean or the expected value of this distribution. Now, the name expected value, I think, is a little deceiving because the expected value, to me, sounds like it's the value you would expect to get. Well, if I played this game exactly once, the amount I'd expect to get was probably nothing, 0. Why? Because there's a 5 out of 8, more than 50% chance that I'll win nothing. But of course, I could win 8 or 24. That's not what expected value is about. Expected value is about what would happen on average were you to play this game a very, 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 very large number of times. If things happen as you expect, how much would you win on average? So to get the expected value, E of X, well, in this case, let's make it E of W. It'll be a summation of every value W times its associated probability for all of the W's in your set. Now in this particular case, this would be some easy math. We could do $0 times 5/8. We could do plus $8 times 2/8 plus $24 times 1/8. And you see why I picked some of the numbers I did, so it would come out all pretty. And when you do some math, you get $5. That $5 is the amount you should win per play of the game. You won't win that on any specific play, but on average, it would come out to about $5 per play. So if you played 500 times, you would expect to win 5 times $500 about total, which would be a lot of money. So in addition to the mean or expected value, this tries to say, what would you expect to happen on average? We also would try to talk about some measurement of spread. So just like, say this is a fancy distribution right here. Say this was average. This is what would happen most of the time, the expected value of some variable X. Then what we want is some measurement to say, how often would you get values close to that? Now, of course, the shape of this distribution has nothing to do with the shape of this guy. This is discrete, this is continuous. But the idea is, how often will you get values close to average? And that's what the standard deviation tries to measure. Standard deviation. Now, of course, standard deviation. Calculating the standard deviation really involves first finding the variance. The standard deviation happens to be the square root of the variance. So we really will always find the variance first, and then if we want, we'll go ahead and find the standard deviation. So to do that, there was actually 2 ways to express that formula. There's the easy way and the less easy way. But the variance of some variable, we'll call it W again, will be the long way in a summation of all your numbers, where you would take the difference between some particular W and the expected value of W, that is the mean, and you would square that difference and then multiply the square of that difference by the probability of that particular value of W. So if we were to calculate this out by hand, it's kind of annoying. We would do 0 minus 5, because $5 was the mean, squared times 5/8 plus 0 minus, excuse me, not 0 this time, 8 minus 5 squared times this time 2/8 plus 24 minus 5 squared times 5/8. And if we did some math, we'd end up getting, what, 125 over 8 plus 18 over 8 plus 24 minus 5 is 19. I forget what 19 squared is. Let me throw that in my calculator. 19 squared is 361. So 361 over 8. And then I could add them up. 125 plus 18 plus 361 is 504. Divided by 8 comes out to, 63. So giddy up. This is 63. All right, so that's one way to get the variance. And of course, the standard deviation would have been the square root of 63. The square root of 63 is obviously, it's obviously a little bit less than 8, 7.9, which would mean while I'd win $5 on average, I would expect any particular winning to vary by 7.9 on average. So that's kind of neat. Let's find the variance another way, though. There's a kind of shorter formula to find the variance of a variable. And this way, instead of doing all these little subtractions, which can get really annoying, especially if you have a very large data set, what we can do is we can find the expected value of whatever our variable is squared and subtract from that the expected value of our variable squared. Now, if you were just listening and weren't watching, you would see it's a little confusing. But you find the expected value of the square of these possible values, subtract that from that, whatever expected value was of our variable squared. So you'll end up subtracting that mean squared. So in other words, to get this expected value of w squared, what we really are doing is we're going to calculate the expected value by first squaring these numbers. So if I went to this distribution up here, I could say w squared would be 0 squared, 8 squared, and 24 squared. Now, 8 squared is 64. 24 squared is a very large number. So let me do that in my calculator real quick. Well, I'll show the work. We'll do 0 squared times 5/8 plus 64 times 2/8 plus 24 squared times 1/8. And I'll just do that in my calculator. That was, so 0 times anything doesn't matter. So 64 times 2 divided by 8. Why did I even do that in the calculator? It's obviously 16. 24 squared divided by 8 is that. So let's sum those two. 72 plus 16 was 88. Okay, so that's nice. So this part comes out to, say, 88. Now, from that 88, I'm going to subtract the expected value of x squared. Now, remember the expected value of x was just 5. So I'm going to subtract 5 squared. So 5 squared is 25. So I'm going to do 88 minus 25, and that's, shazam, 63. So we got the exact same variance of 63 and the same standard deviation. So hopefully that was a helpful, nice little example of how to calculate some of these things. Hopefully you can read my handwriting, and hopefully you have a beautiful day. Giddy the heck up. Enjoy.